Hello, I'm Álvaro Fernández Casaní. Today I will be presenting the work titled Big Data Analytics for the ATLAS EventIndex project with Apache Spark. Okay, so ATLAS is one of the 4 bit detectors of the Large Hadron Collider at CERN in Geneva, and is recording events or particle interactions devoted to the predictions of the standard model and the development of new theories. It's a distributed collaboration with multiple centers around the world, so data is recorded at CERN and distributed to this center worldwide using grid technologies. So one of the tools that we have is the ATLAS EventIndex, which is a catalog of data that records and is able to access all the events, real and simulated, in all precision stages. The data model is that events are stored in these files distributed in the grid, identified by grid. Files are grouped into datasets, and datasets are grouped into containers. We are indexing a small quantity of data per event in the order of 300 bytes to 1 kilobyte per event, and that contains the event identifiers, the online trigger pattern, so the combination of the signals that made the detector record the event, and references to the file in the physical file, to the event in the physical files. During the run 2 up to until 2018, we have been indexing in the order of 30 billion of events and storing in CERN Central in a Hadoop database. And now that we are starting run 3, and for the next run that we are increasing the factor, we have been redesigning the system using new tools. So the use cases that we are solving are basically event picking, selecting particular events from those billions of events, then production consistency checks for checking for duplicates across different granularity of files or datasets, and producing this kind of matrix for detecting the overlaps of events across several streams. And then for triggers, the same, using calculating some statistics for the triggers and also overlaps among different triggers of different datasets. So we're using Spark in several forms. First, for the data ingestion of the data that is recollected distributedly by the data collection task. But this talk is about the data access to this data using Spark in an interactive and batch way. And we are accessing the data that we have in the backends. First, we have the data in HDFS, and now we have moved the data to HBase, which is a key value storage, and which is in principle a schema list. But with Phoenix, we are defining a schema and providing SQL-like functionalities. So Spark is able to access the resources provided by Yarn in a cluster, and with our tools, we are analyzing and solving these use cases. So we have defined several data tables in Phoenix. The big main one is the events, where we store the billions of events, one record per event. And it's mapping the key value form of HBase. So we are using a compact key with several fields. First, the dataset identifier, the SPID and the type ID, the event number, and a sequence, which is a hash that allows us to store duplicates. And we're using fast HBase get operation for single events, and also we can use scans over the key for solving the derivation on overlaps use cases. The data in the values is stored in several families, so we group the data in kinds of data that we are accessing, so we only need to access some kind of data. In this way, we are reducing the input-output, and we're using columnar storage. We are allowing to use better compression ratios. We are defining this for families, or event location, event provenance, L1 trigger, and L2 trigger. Then on the data model, we are defining datasets and container tables. And here the idea is that we have in the key all the fields that are able to find these datasets, so run number, project, stream name, step, data type and version, and then it refers to the events table in this way of DSP ID and this type ID, which are filled as a foreign key to this events table. And then we record some summary regarding the information in the number of events, duplicates, files, and so on. Okay, so for testing, we ingested an amount of data using the CERN Analytics production cluster, which is composed of 59 nodes. So we use a MapReduce procedure to move data from production ATFS to the new H-based Phoenix tables. So we move to the order of 70 billion events, and we were writing in the order of 115 kilohertz in events per second. The results were in this events table, occupying 22 terabytes in 4 families, and as you can see, the event location and event provenance family has the less data, but the trigger ones, family C and D, contain most of the data. So the tools that we are providing are implemented in Scala using Spark facilities, Spark functionalities and abstractions, and as you can see here in the screenshot of an interactive session, we are importing our tool, and then using the find canonical function, we are obtaining the data that is stored in the canonical datasets table in a form of a Spark data frame that is inferring the data under the data model. So this is done dynamically, and we can apply functions, a Spark function, like for example count, to check the number of data sets, and then a SQL-like function like group by project to check all the events or the data sets that are in the datasets table by project. Another possibility is to refine the previous canonical data frame that we have in Spark, for example, using where and select clauses. And this example, we're checking for the datasets that are belonging to project MC16 at 13 TB and that has trigger, and selecting the dataset name and the events. For checking the events and duplicates, we can refine for the previous canonical data frame, and applying the find events, we will obtain a new events data frame with, which has inferred again the format of the table below, so we have all the fields accessible, and for example, we can access the number of events that are already available, but for the number of events duplicates and events unique, so duplicates related fields, we have to calculate it, so our tool calculates it on the fly, as you can see here. We have applied a Spark application, we have submitted a Spark application to check for the previous fields, and also providing a list of files that contains duplicates, and we have applied this tool for different kinds of datasets with 200,000 events, 1 million, 20 million, and 100 million events. So we measure the times. We have this linear performance starting for the smaller dataset with 1.5 kiloevents per second, up to 120 kiloevents per second for the biggest dataset. We have benefited for Spark tools and configuration, as in this case, this is configured to auto-scale automatically to 32 executors, so it scales correctly linearly. We haven't seen any difference in processing the number of duplicates, in the number of times. So was accessing some trigger. In principle, when we tested it was not possible because of limitation of the Spark implementation. So we solved it in the code and submitted to the Apache, and was finally accepted. And this will be ready in the next official Apache Phoenix releases. Our last use case is the overlaps calculation. So in this case, we are producing this matrix of overlaps. So we have in the order of millions of events, and we want to check the overlaps of these events in several streams that are in the order of 100. So we are producing this S by S matrix with our tool that in this case is producing a a Spark data frame, again, that has one entry per pair of streams, so we have to calculate only the number of independent entries on this symmetric matrix. We are calculating the elements, the number of events that are belonging to stream 1, to the second stream, and with both streams, and calculating the ratio as the intersection over the union. So the algorithm has 4 main steps. We have to go through all the millions of events that we want to check, but we have to only retrieve the information of the event number and the stream that is in the data type, and all this information is on the key, so it's the fastest access that we can have on HBase. The second step is to group the streams by identifier. And then for the third step, we are producing all the pairs of the streams that contain this particular event. So this is the most intensive step, because we have to go over all the streams, and as we can see, can be in the order of 100. So we are producing these tuples with the pair of streams identification, and if the booleans that represent if it's in one or in the other or in both. And this information is reduced in step 4, where we group by pairs of a stream, counting the number of the previous generated values and producing this final S by S matrix, counting with that this is a symmetric matrix. About the cost, we are playing the algorithm, submitting some applications over different sets of data sets in the order of, again, 200 kilo events, 1 million, 20 million, 100 million and 500 million, and divided into a number of streams up to 83 in this case that was available. The number of computations is the number of computations is n as the number of events per the number of computations that we have in step 3. In this case, the dominant term is n, so the temporal cost is in the order of n. The intermediate data produced can be at most into this number of computations, so a high number of produced data, but this is reduced continually in step 4 by Spark partition, so the final cost is quadratic related to S. And about the overlaps calculation time, we can see in the figure on the left, on the blue, this is the baseline for one stream where we don't have to do any calculation. We can see that goes up to 1,200 seconds for the 500 million data set. And for the rest of the stream, we can see that for up to 1 million goes very similar, and then goes linearly because and goes with the size of the problem, and the number of streams doesn't affect too much in the performance. And on the right, you can see the calculation rate that goes up to 380 kilo events per second processed for the bigger data sets. So as a conclusion, we have presented this tool for analytics over our data using Spark tools. This provides us a abstraction of the backend data model, and this can be run in an interactive or batch way. For the capabilities that we have on this tool is data discovery capabilities, and we are solving the overlaps and duplicate cases. For overlaps, we only have to access the key, so we have scan, we can apply scan operations which are pretty fast. And for duplicate detection, we have to access an extra family, which is the location for the files, and we are accessing more data, and therefore we have a bit small performance. So in general, we have variable processing rate with better rates for bigger dataset sizes. So in general, we are incrementing the Spark job granularity where possible, and this is solving correctly our use cases with this tool, with Spark. So this will be all. Thank you very much for your attention.